Hi guys, welcome to this lecture number 24, I guess, right? But so it should be lecture number 24. If I was numbering all the classes, it would be lecture number 24. Although, of course, we didn't have slides for a lot of the classes. Anyway, Computer Science 330, November the 10th, 2020. Today, first off, I want to make an announcement. I have updated the syllabus. It's not uploaded to the Blackboard yet, but a couple of things which you need to know. In the opportunities to earn extra credit, there is a new section. Well, first off, all of the opportunities to earn extra credit are valid until the reading day. After that, I will not be able to process a lot of emails. I will not be able to give you any amount of extra credit. So here's what I added. There will be a few logical thinking math probability geometry problems available on the YouTube channel. You can solve any of them. I have already prepared 9 of them. Okay, so this one, which you're going to see today, is the first one. It's a logical problem about 2 candles. Okay, so you're going to solve that one first. Try to solve that. Okay, so you can solve any of them. I have already prepared 9. I have already recorded them. They will slowly appear on the YouTube. And present your solution to me, proving that you solve that yourself. Okay. Be ready to answer additional questions. Each one of them is worth a different amount of points depending on the difficulty. So, for example, this one about the candles, this one is the easiest. I think almost the easiest one. It's worth 0.5% of your final grade. But there will be a couple of problems which are more difficult. So I'll be able to give you up to 5% of extra credit for solving them, right? So I think there is one problem which will be like 3%, another one will be 2%, like 1.5. So you can solve all of them. That'll be very cool. Please do not spread the solution, by the way. And I will be able to give you 5% of extra credit. Okay, hope it makes sense. They are a lot of fun, in my opinion. So please go ahead, knock yourself out, take a crack at it. Okay, anyway, today we'll be talking about control theory, and well, first off, we'll talk about what is simulation, what is animation. Okay, so simulation is the imitation of the, so I'm going to introduce a couple of terms which you guys will definitely need for the final exam. Simulation, what is that? It's an imitation of the operation of a real-world process or system over time. Okay, imitation of the operation of real-world process. So it's very important. Simulation is something which is run on your computer and it imitates as closely as possible a real-world process. Okay, so that's what simulation. And what is animation? Animation is just the process of creating a continuous motion. Okay, so animation, like Minions, right? Any Pixar cartoon, any cartoon is just an animation. Of course, it does not animate. It doesn't have to simulate anything, right? So you can draw whatever you want. You can draw a basketball. Somebody throws a basketball, goes into the space. That's of course impossible. So that will be just animation, not simulation. Okay, so please learn those terms. Okay, so that's kind of the real-world system. So that'll be animation. This will be kind of simulation, right? So a person is swimming, okay, doing backstroke, or just like swimming on the back, and we kind of trying to calculate, I don't know, water resistance or something like that. Simulation is the imitation of the operation of the real-world process. Animation is just the process of creating, again, continuous picture. Okay, illusion and shape change illusion by means of rapid display of sequence of static images. Okay, that's how usually like the movie works, and that's how your camera works on your iPhone. It just captures 24 pictures per second, shows them to you like 24 pictures per second back, right? And you kind of see that something is moving. So question, is there a difference between a simulation and animation? So obviously yes, there are quite a few, right? So simulation, kind of the whole purpose is to create a scientific evidence. And animation is just a moving picture, not intended to simulate an event. It is generally detailed, right, and realistic. It is to recreate computer image of an event that can be manipulated. And for animation, authenticated by sponsor and witness with personal knowledge of the content of the animation, right? So this one is more scientific. This one is, you can animate whatever you want. Simulation can be portrayed from different angles. or from viewpoints of different witnesses. Animation is usually not that complicated, it only shows that it fairly and adequately portrays the facts. Okay. So again, if you throw something up, then it should at some point come back down. That's how it works in animation. Simulation should be scientifically, it should scientifically measure the distance and the height and the speed of the basketball which you're throwing up. Embodiment, having a physical body that occupies space in the physical universe, right? So in the physics, there will be the embodiment, physical limitations, time, right? So they'll be related to the embodiment and personal space. For simulation, we need sensors, technically. And sensors are physical devices that enable a robot to perceive its physical environment in order to get information about itself and its surroundings. Simulation, okay, so there is a huge difference between sensing and perceiving, sensing and perception. So what is sensing? Sensing is just an ability to detect, capture changes, and provide corresponding output. So for example, if you have a wall sensor, right, so the wall sensor senses how far away the wall is, and it provides you a number, gives you like the number between 0 and 1023. The bigger the number, the further the wall is. And perception is more complex. It's an organization, identification, and interpretation of sensory information in order to represent and understand the environment. Okay, so perception will actually understand that there is a wall, and you need to avoid that. Not like something next to that, but actually it has to be a wall. So sensors are needed to perceive the environment. Okay, so I guess sensing would be would be part of perception. Moving on, effectors. An effector is any device that affects the physical environment. Okay, so for example, a wheel, when it spins, it moves you into the environment, or it can actually hit someone, and it's going to affect the environment. Legs do the same thing. Arms, flippers, they kind of flip the water. An actuator is the actual mechanism that enables the effector to execute an action. Okay, so something which is actually moving the effector, that's called an actuator, for example, an electric motor. Or hydraulic cylinder, or what else? Pneumatic cylinder. Pneumatic. Okay, so actuators, activities, and response, a corresponding subfield of robotics. For example, if we're talking about locomotion, in this case, corresponding subfield of robotics would be mobile robotics. Okay, for manipulation, we have manipulator robotics. Mobile robots use their effectors and actuators to move the physical embodiment of the robot. Okay, hope it's obvious. So the only purpose of me reading this, I just want to, well, make sure that you understand that, although it's not that difficult to understand, to comprehend. But please make sure that you know these definitions for the final exam. Controllers provide the hardware and the software that makes the robot autonomous by using sensor input and other information. Okay, so the controllers perceive, right? So they get the information from the sensors, and then they do the entire perception. So they decide what to do, right, based on the sensing something, and control the effectors and actuators to execute the action. Okay, of course, in the body, we have a brain, all the nerves, spine. Like, think about how many nerves we have, right? So that's all, of course, a part of controller. So the brain is controlling, and like we sense through the nerves, and we transmit the message about any pain, either cold or heat, through the nerves. Okay, hope it makes sense. Yeah, so from this section, you just need to know only definitions and I guess understanding of how everything works. Moving on to the next part, control theory. Okay, and that's what you are going to need for your project. So control theory, what is it? What is it? It's basically a part of, I guess, electrical engineering and computer science and a lot of other things. Maybe it's in the science by itself. I don't know. But imagine you have a basketball, right? And imagine you're throwing that somewhere, and imagine that somewhere over here we have a rim, right? You have a rim, which is, well, let's not do that. Okay, so you have a rim, right? And you're playing basketball. So the idea is that, so what do? You throw a ball, right? And imagine two situations: you're throwing a ball with your eyes closed, and you're throwing a ball and trying to make it, of course, and you're throwing the ball with your eyes open, right? Of course, the probability of you making that after a couple of attempts is much higher when you have open eyes. So why is that? The idea is when you throw when you're trying to throw a ball, your muscles have some kind of memory, right? So you memorize the movements of those muscles, you throw that ball, and that kind of goes into the dream, into the loop. And based on what you see, based on if you made it or not, based on if you throw it to the right or to the left, or if you fell short, if it fell short, right? Or like if you overshot it, which means like it went much over the rim, right? It didn't touch it. In this case, that reality gives you the feedback. So let's make it something like this. So that's the reality, right? That you seeing that gives you feedback of what you did wrong. In this case, that feedback goes back into your nervous system, and your brain decides what to do next time in order to improve the result. Okay, so for example, if you fell short, right? So for instance, if you like fell that way, right, fell short, you see that, and you immediately understand that you need to throw that ball stronger, right? You need to apply more force. So your neural system tells your arms to apply more force to get it stronger. And next time, for example, like you overshoot it, right? It goes that way, and then again it gives you feedback back to your brain, to your neural system, saying that like you overshot it. You need to make it in between this attempt and that attempt, and maybe like third time you make it into the rim, which is perfect, right? So you always receive feedback from the reality, and it's you kind of have a cycle, right? So let's make this color. Okay, so it kind of creates a cycle. So you do something to the environment, and the environment gives you back the feedback, right? It gives you some, yeah. So and how do you do that? You sense it with your eyes. Okay, so that is something which is called the feedback loop, and that is something which is very important in the control theory. So it's called feedback loop. Okay, so that loop. And of course, that's impossible if your eyes are closed. You throw it. So even if like you, I don't know, spend 20 years playing basketball, right? You throw a three-pointer, and it's possible you did it wrong, right? But let's say like there is someone, so you can't see that because your eyes are closed, right? Someone tells you that you made it wrong, right? And in this case, like you didn't make it. In this case, you don't really have any feedback from the outer world. You have no idea what to change. So what you're gonna do? You're gonna just keep doing the same thing, or maybe again. So somebody telling you that you did something wrong is already feedback, right? So if you don't have that feedback, you'll just be throwing the ball with the same force, exactly in the same direction. You'll be just trying to repeat exactly the same thing, having no idea if you made it or not. Okay, so that's what happens when you do not have a feedback loop. Okay, so that's strictly not desired, right? When you don't have the feedback from the reality, that's not desired. Okay, so in our case, what do? We have a wall. Okay, so we have a wall, and we also have a robot. Okay, so you align it, and you kind of asking it to move that way, right? However, obviously, in reality, although the robot is moving its muscles such that it should move forward, you of course understand that it's not going to move like strictly forward, right? Because of the physical things, because of the like margin of error in the speed, it's going to move left or right. So at some point, it's possible that it's going to like go that way, right? Or it's possible it's going to go that way, like if robot is completely broken. Yeah, so that's undesired. And in order to avoid that, yes. So what's the problem? If you want the robot to move with a certain distance within the certain distance from the wall, right? What are you missing? You're missing the feedback. So you have like, for example, 5 seconds left, 5 seconds later, when you're somewhere here, you have no idea where you're located, right? So you know that you started from here, but and you know that you supposedly should be going somewhere there, right? But there is nothing which can tell you that you made a mistake, unfortunately, and that's a problem. And why is that? Because you don't have any feedback. You don't have a feedback loop, right? So the brain of the robot tells it to drive forward. It doesn't receive anything back, any information back from the environment, and it doesn't know how to correct its actions. And that's exactly why we need the sensor, right? So the sensor is going to always tell you if you're doing right or wrong. Okay, so I explained it informally. So now let's get to the formal definitions. Well, first off, a couple of pictures. So control theory origins were, in comparison, an attempted implementation of artificial systems based on biological systems. By mimetic system imitating biological processes, the robot consumes and digests organic matter for energy. First system fulfilling all requirements to be a robot. So, excuse me, that's what you're probably thinking of being a robot, right? So the guy can actually walk, he can sense the environment, he can make all decisions by itself based on the feedback it receives, right? That's the idea. Okay, so that one, kind of the first robot, what was it doing? It was described as attracted to strong sources of light, contained two photovoltaic cells, right? So they were converting lumens. It was converting light into volts, into voltage. Two-wheel motors acts by moving forward toward brighter source of light. Okay, so the idea is to convert lumens to centimeters per second while providing a phasing. Okay. Yeah, so that's pretty much it about the control theory. So what do you need to know? I want you to watch these two videos. Oh yeah. So what we'll be using in this project is called something which is called PID controller. PID controller. Okay. Let's change this. Okay. Okay. No, hold on. PID controller. Okay. So what does it stand for? PID is an acronym. P stands for positional, integral, derivative. Okay. I hope I'm spelling that correctly. How to spell derivative? Hold on. Derivative typically works. Okay. Yeah. Sounds like I'm correct. Okay. Oh, it disappeared. Okay, PID again. No, hold on. Okay, whatever. Positional. No. Sorry, 1 second. PID. Oh. Okay. So positional. I'm so sorry. Hold on. I'm overthinking the whole thing. Okay. Okay, so PID. So positional, integral, derivative. Okay. So the idea is that how can you take the input from the outer world and you can change for example, your position, if we're talking about the position, right? So there is a huge amount of controlling systems. The most primitive one would be just P controller without ID, so just P. Okay, so that means it's only going to change the position in the most naive way. So what does it mean? Getting back to our example. So let's say that's a wall, right? And let's say we have a robot. Okay, so the robot moves over here, and we have the wall sensor. Okay. So the wall sensor is located over here, and it's trying to sense the environment. Okay, so when you test that, you'll probably see that the ideal value for that sensor is something like, let's say, 100, right? And let's say you always want that sensor to feel 100. So you always want the distance between the robot and the wall to be constant, and the sensor should always sense 100. No, like it doesn't really matter what it translates to, but I think like I remember 100 being the best one, like one of the best values. Okay, so let's say that that's your decision. Okay, and the idea is that every single iteration of like a while loop or every single discrete moment of time, for example, you decide that you're going to feel the wall, sense the wall every other second. Okay, so a second later from that moment, you will be located somewhere here. Okay, and you're going to sense the wall again. So if you sense in 125, for example, that means you move to like 25 to the left, right? So for some reason you move over there, and that's not what you wanted. In this case, what are you going to do? You're going to take the difference, 25, and you're going to convert that difference into the speeds of the wheels. Okay, so for example, you're going to change the 25, you're going to multiply it by some coefficient, let's say, I don't know, like 0.1, right? So you're going to take 10% of that. And you're going to increase the speed of this wheel by 10%, you're going to decrease the speed of this wheel by 10%. In this case, this wheel will be moving quicker, okay, creating more force, and in this case, you're going to go back to the wall, okay? Of course, and so this wheel will be moving quicker, this wheel will be moving slower, which makes you turn right, a little bit to the right, and vice versa. For example, a bit later, maybe 1 second later, you're gonna sense it again, and you're gonna feel, I don't know, let's say 90. Okay, so you know that 90 is not like exactly 100, and that means you kind of moved a little bit to the right, which is bad, and you need to move back. Okay, so what you're gonna do? You're gonna compare 90 to 100. You will know that the difference is 10, and in this case, you're gonna increase the speed of this wheel by 10, by let's say like 1, right? So if you multiply it by 0.1, and you're gonna increase the speed of this wheel by also 0.1. Okay, yeah, sorry, 0.1 of 10, which is 1. Okay, and that makes you move that way to the left. So this is considered to be the most trivial, the most naive, only positional PID, right? So only positional. So you only the decision of what you should do with the speeds of the wheels only depends on your current position and on your previous position. Not on the previous position, only on your current position and on the ideal position, which is 100. Okay, so that's considered to be the most naive, and yeah, and that's why it has a lot of mistakes. The idea is that it can't really adjust to the system. It's not the best one, and that's why they created something which is two other components, which are called integral and derivative. Basically, integral is going to calculate the integral of all of these differences, and derivative is going to calculate the derivative of all of those differences summed together, and there's going to be like quite a complicated formula, which is going to basically magically add up to the right number which you need to add, and that's going to be much smoother of a movement. Okay, so I'm not going to explain you what integral derivative yet. I want you to, I'll do it in person. I want you to watch these two videos. I want you to watch this one, PID control, a brief introduction, and I want you to watch the one after that. This guy probably has the best explanation I've ever seen, and I'm going to explain to you one more time. And I'm going to explain to you one more time and what it means to us. How can we change what we How can we translate what he's talking about? How can we translate integral and derivative portion into our example of PID, into our project? Okay, so that's our plan. So please watch these 2 videos. Okay, I'll see you on Thursday. By the way, you will need all explanations. You will need to know them for your final exam as well. Okay. Yeah, that's it for today. I hope you guys enjoyed that. Please have fun. The project will be due on Tuesday, right? So on Thursday we'll still work on it. On Tuesday we're gonna have a demo day. Yeah. So I'll see you guys later. Bye bye.